today I want to talk about their dynamics and what their orbits around the sun tell us about their future, their present, and their past. And so one of the main tools we use for this is asteroid family age dating. And so basically rewinding the solar system over hundreds of millions of years or billions of years, backing it up to see what happened a while ago and what stage the various things happened and how that influences what the solar system looks like today. So to do this, we have to go back to orbits because orbits are where it all starts. Once we have a well-measured orbit for an asteroid, we know its path around the sun for quite a while. There's no friction in space, there's no EM, there's really nothing but gravity controlling the orbits of these bodies. And there's a big asterisk on it that I'll get to at the end of this talk. But gravity dominates their motion. And Keplerian gravity, except for Mercury in there, Keplerian gravity is pretty much all you need to do a lot of these simulations. So we can study their dynamics through what are fairly simple codes, stuff that you learn in high school or college or first year college. Keplerian dynamics, basic gravitational forces on a very large scale. Because now we have, instead of one massive body, the more detailed simulations deal with multiple massive bodies. The gravity between all of these things simultaneously. And so that's where the difficulty comes in, but that's also where all the information we get comes from. And of course, asteroid dynamics and orbits are really interesting to a number of people, including one of the best villains in all of literature. Does anyone know who Professor Moriarty is? Yeah, that's Sherlock Holmes' main opponent, and this is the book he had just written when he first meets Sherlock Holmes, on the dynamics of an asteroid. And so asteroids inspire a lot of stuff, including one of the greatest villains in literature. So I always liked that Moriarty was an asteroid scientist. Makes me, I don't know.
Are you a villain?
No, I'm not. That you know of. So, again, let's go back to the main belt because that's where we have the largest number of objects, and that's a stable region of the belt, right? So we have long-term stability over 4.5 billion years. Objects in this region are only stable on the couple million year time scale. Stuff in these resonances is stable on the tens of thousands of years time scale, but the objects in here are stable over billions of years, and so the structures you see are long-term structures. And we see this very clearly in our plots here, but these concentrations of objects were noticed quite a while ago. In fact, they were first noticed over 100 years ago by Kiyotsugu Hirayama, who put this paper out in 1918 in AJ that just said groups of asteroids probably of common origin, which seems pretty obvious now, but was a huge leap at the time. And it took another 50, 100 years to start putting all the pieces together and say, yes, they are of common origin. Yes, they are groups that are related. Yes, they are of common origin. But it was just so obvious from the early dynamics. And the way Hirayama found this was looking at so this is a really strange plot. So this is the U and P planes of the object. So we're not looking at orbits around the sun. Instead, we're looking at pole position of the asteroid's orbit. So if you have the elliptical orbit, you ask where is the north pole of that orbit, and you plot that in a velocity vector plane, you put the sun over here, and you have Jupiter over here with the sun at the center, and he saw that these objects they seem to follow a circle around, in this plane, around the orbit of Jupiter. And he found a couple of families, so the Coronis family, the Eos family, and also the Themis family, so the three main families in this paper. And he said, oh, well, look at this. All of these things have poles that look to be related, and they look to be cycling around Jupiter. So that Jupiter's gravity is causing them causing the orbits, not the rotational line, but the actual orbit, to precess. And so as Jupiter forces that precession, things with very slightly different initial conditions will spread out along the circle. Some will precess a little bit faster, some will precess a little bit slower, and so you take what was originally something of everything on the same orbit, and you slowly spread it out over cycling until you're left with a ring in this velocity space, basically. There were also clusterings. What this is showing here is that's a clustering in rate of motion per day, average rate of motion per day of the asteroid, so the mean motion we call it, which winds up, when you do the Keplerian dynamics, is just the inverse of semi-major axis. so the inverse of average distance from the sun. And so what he was showing here is that you have a cluster of objects at similar distances from the sun that all look to be that have started at what was the same orbit and then precessed. And so that's how you come up with the idea that, all right, these are groups of objects, and they probably had a common origin. Because if you just let this go long enough, eventually they're all going to come back together. And so, all right, so these things started together and have spread out over time. What's really impressive is all of this work was done with less than 800 asteroids known. We have a catalog of 800,000 now, and we're starting to look at more of the family dynamics, but already, with less than 1,000 objects in the catalog, these trends became apparent. And so what that says is Hirayama was really good at doing the math and noticing these trends, but also that families dominate the asteroid population. That they are not some random small component, that they are one of the major components of this population. And especially the three families that he found, Coronis, Eos, and Themis, each of these have thousands of members in them out of the top 10,000 asteroids. So they represent a large fraction of the belt just in these three families. And so this of common origin led to this picture, led to the view that an asteroid family was a single large parent body, and something slammed into it and caused it to shatter. And what that mechanism of shattering is, and how the physical processes aren't quite clear, because these are impacts at a scale that we can never simulate on Earth. We can do gas gun experiments to try and simulate craters of the moon by taking a big flat sheet and firing a bullet at it at a couple, 5, 10 kilometers a second, making a crater, and this would be what a small meteoroid hitting the moon would make, and you can say, okay, you can scale it. But something where you have an object of comparable size to an asteroid crashing into it at 10 or 20 kilometers a second is something we can never simulate in practical reality. We're starting to do numerical simulations of it, but now you have to worry about what's going on the inside of this object as all of these stresses and forces and heat are being transmitted through it. What's the internal equation of state of these bodies that maybe never melted? What's the inside of an asteroid look like? And so that's one of the reasons we like studying the families, is they are the remnants. So by taking all these pieces that get ejected off, you can look more at what that exact process happened. And so you can start to actually have evidence for what the largest collisions in our solar system have occurred in the last 3.5 billion years look like, what their physics looks like, what their outcomes look like, how often they happen. So we can take the asteroid families, and I've shown you this plot before. This is against semi-major axis against orbital inclination. Here what I've done is I've taken all of the asteroids in families and plotted them here, and all of the asteroids that we can't directly associate with a family, and put them over here. And the reason to do that is asteroid families represent, as I said, about a third of the population that we know about right now. And so something like the Eos family here can change your number statistics when you're looking at what does the background population look like. And so by pulling out the family, we can now have a better handle of what's the background. Because the question we want to answer is, what did the asteroid belt look like when it formed? Did it form a distribution of sizes? Everything from a Ceres-sized body down to pebbles? And that has evolved over time into what we have today? Or did it form just a handful of, and by handful I mean a few thousand, 100-kilometer things, and nothing smaller and nothing bigger? And it's those things that evolve, some of them growing bigger, and many of them shattering and growing smaller. So if we take out the things that were generated in collisions in the last billion or 2 billion years, we can now see what's the underlying population look like. And already, if you look carefully, you can see that this family selection mechanism we used isn't perfect. There are still some of these purple points left here that look like, due to their composition related to the Eos family. You can see that this cluster, this family up here is a nice tight cluster, but it pretty clearly looks like all of that should be part of it as well. And so there's still work to do in how do we correctly identify what's attached to a family and what's not. And the way we do that currently is called the hierarchical clustering method. So it's referred to as HCM, and what it does is it tries to look for overdensities in a 3D region of space. And so we take the semi-major axis, the eccentricity, and the inclination, we populate this box with all of the objects in the orbits that we know of, and then we look for orbits that are close to each other in 3D space. You can also add extra dimensions. You can add the albedo of the object. You can add colors if you have them from the Sloan Digital Sky Survey. You can add a range of other parameters trying to narrow down this window, but fundamentally what you do is you start, and for every object in this field, you ask for a certain velocity distance, and that's basically the distance in velocity space between the two orbits. Does this object have any neighbors? Is there anything within some random velocity cut? If so, group them together. Take them, add them, and now you have a cluster, and then ask the same question of every object in that cluster. And then do it again, until you add no new objects to this cluster. This is now your asteroid family, which is a slight overdensity compared to the background. And so what you then do is you look at a step through a range of velocities and ask, all right, how do these families grow? Small velocity steps will make very tight clusters. If you pick too big a velocity window, you'll gather the entire main belt into your simulation. And so where you cut becomes a bit of an art. You can do semi-deterministic ways of saying, okay, if I had a random belt, what would I connect together? But what you can do now here, so I'm showing, this is just number of the object. You don't have to worry about that, but this is the velocity cutoff. So for each velocity window, how many objects cluster together? And so these clusters start to come out. So you can see as you go up in velocity space, down here at 15 kilometers a second, you have a couple of very tight clusters. And as you look at wider and wider windows, you get more and more families appearing. This one here, so these numbers are the number of the asteroids. So this is the family associated with Vesta. And so you can see it's not as tight a family, not as tight a cluster as the other ones, but it quickly grows, and at too big a velocity cut subsumes half of the main belt. And so again, how you select where this should be, where do you accept, all right, everything below this line is a member of the family, everything above that line is not. Depends a little bit on what your simulations are for what would a random population of the belt look like, and is a little bit of by-eye tuning. So you go in and you say, this looks like it is, this looks like it isn't. You look at the slope of this growth here, and you can say, all right, this is growing too fast. Well, as soon as the slope, it should peter out, and then when it steps up like this, all right, I can cut there. That's a good, reliable cut. But a lot of this is somewhat subjective. So this is why in that earlier plot I showed, there were things that looked to be clearly part of the family via composition that weren't included. And it's either because we chose too conservative a velocity cut, or that some objects have spread so far that you can't distinguish through this method them from the background. Now, I said that right now, this is how we find asteroid families. But we're rapidly approaching a point when we can't use HCM anymore. And the reason for this is number statistics. If you have a general 3D box, as you put more asteroids in there, as your catalog grows, the background density of those objects grows too. And so that means you start randomly connecting asteroids at lower and lower velocity cuts. And so something that may have been apparent when you knew about fewer objects will vanish just because your catalog grew. And so every time a new asteroid is discovered, you have to rerun this analysis and recalculate what's my optimal velocity cut for that population. And so in the era of upcoming large surveys, that's not going to be a feasible method. And so people are starting to explore new methods of how do you build asteroid families. And one of the most promising is statistical identification of the families. So this is some work Kevin Walsh did a few years ago. And distance from the sun and semi-major axis here, and absolute magnitudes, this is the HV parameter, which winds up being effectively an inverse diameter. So this is right around objects that are about 1 kilometer in size, getting bigger and bigger and bigger, until you get here where you have objects in the 50 kilometer range. And so this shape you see here, this open double-winged shape, is typically what you would expect if you had one large object that broke apart and and the pieces spread out in space, you would expect to get this kind of shape. So what Walter's group did is look for overdensities by searching for objects that fit this parameter shape here. And so this is a particularly tricky region around the asteroid Polana. It's a low albedo asteroid in the inner main belt. And this is what HCM would come up with. It's not able to distinguish the difference between this population. It accumulates all of them in the velocity space with this one parent. But if you do a statistical method where you ask, as I move these wings up, as I dial different velocity spreads, and as I dial different semi-major axes, looking for an edge, looking for something where there's more on this side than that side of the line, you come up with these two subfamilies. And this is something that your eye naturally picks out. If you look up here, yeah, it's pretty obvious that there's a line cut here, and that there's a second thing in here. Now, where that is in relation, is this a different family? Is this a younger version? Is it the same object was hit twice and has a younger thing and older thing? You can only find with this statistical method. And so in this case, they're able to associate this blue curve with the asteroid Polana and this overdensity with 495. However, the reason I call it a statistical association is for an object that falls in here, you cannot distinctly say, is it part of this family or that family? And so if you want to study its composition, if you want to study what Polana looked like before the impact, what was the thing that it was originally when it was a single body prior to it getting impacted, you don't know what to include in that analysis. So you know that stuff here is in one of the two families, but you don't have this deterministic thing that the HCM method gives you. And so there's definite benefits in identifying families that were missed, and there's drawbacks in that you can't necessarily do the same analyses. And so we're starting to have to come up with new methods of identifying families and associating objects with families. And this is actively being researched right now. And could be something that, it is an avenue that in the upcoming future, as we have LSST and NeoCam and new surveys coming on, we will need new people to help come up with these new methods. And those could be you. So all of these plots have been shown. So the semi-major axis here and the inclination eccentricity have been proper orbital elements. And I talked a little bit about them before, but let me go into a bit more about what the different kinds of orbital elements we can use. So in general, if you look at a catalog of orbital elements from the Minor Planet Center or from the JPL Horizon system or from the European ASTIS system, they will give you what's called an osculating orbital element. And so the osculating orbital element is an orbital element that is valid for a single time. Because 20 seconds later, this asteroid gets perturbed by something. Usually Jupiter, sometimes Saturn, sometimes a terrestrial planet if it's an near-Earth object. But these osculating orbital elements are the instantaneous values of the path of the object around the sun. It's the instantaneous XYZ vector and VX, VY, VZ vector. But they don't tell you necessarily where the object will be in the future, only where it is right now and how it's moving right now. There is a perturbed orbit, the true orbit, that's what happens after this object, after you do the gravitational interaction between these objects, that the true path the asteroid will follow. So the osculating orbital element is an instantaneous estimate. And as a funny note, osculating means to kiss. So these are the orbits that kiss the true orbit, its true semi-chaotic orbit around the sun. I don't know why they chose osculating for this, but it was probably poetic. These are great for navigating spacecraft because you want to know where you're going right now. But it's not so helpful when you want to do family studies, when you want to say, what's the average position? So instead, we look to proper orbital elements. And so what we do is you can look for a time average of the oscillating elements, trying to remove some of the basic perturbations. And by basic, I mean the forcing by Jupiter. Right? So when you saw in that first plot by Hirayama how Jupiter was forcing these objects, the poles of their orbits to rotate, you want to remove that. You want to take this out. You also want to take out the Kozai resonance. This is an energy interchange between eccentricity and inclination. In the outer solar system, this can cause things to go from highly eccentric and flat orbits to very circular and highly inclined orbits. It also happens in the inner solar system, but it's usually a weaker effect than gravitational domination by Jupiter. But you want to take out these things that change over time but in a repeatable fashion to look at what's that average orbit the object should have. So when you do this, though, the average orbit doesn't necessarily have an argument of perihelion or longitude or longitude as a node that makes sense, right? So asking for an average orbit, where is it closest to the sun? And for an average orbit, where does it come up through the plane of the ecliptic, isn't a useful constraint because it can have any value for that average orbit. You don't average over the argument of perihelion and longitude of as a node are the first things that get moved around by perturbations. And so they encode the least information in these long-term studies. So they don't have a meaning, really, in proper orbital elements. Likewise, neither does the mean anomaly, neither does the position of the object around the orbit. We don't care about that. All we care about is how big is the orbit, how elliptical or circular is the orbit, and how tilted is the orbit. And those are the three parameters that we're looking for with proper orbital elements. So that's why we only use A, E, and I. And so, for example, this is a calculation of effectively the instantaneous proper eccentricity of an asteroid without accounting for the perturbation, before you remove a lot of the perturbations. And so, if you were doing, so by eye, you can tell that the average eccentricity of this object is right around there. But you have to make sure you observe this over a long enough period. We can only tell that because we did our calculations over a long enough time baseline, in this case 2 million years, to see a couple of variations. If there was another order term, for instance, if there was something in the solar system that was causing a periodic variation on the order of 10 million years, then we would never be able to see this in this analysis. And so calculating proper orbital elements from that would effectively blur your solution. It wouldn't give you the information you want. So you have to make sure you look at this over a long enough period of time. But what you get is, instead of having this, a measurement that varies from here to here to here over a few million years, you basically pull the belt into focus. And so you go from something like this, showing eccentricity against inclination and osculating elements, to this, proper eccentricity and proper inclination. Same data points, same orbits, just a different way of calculating what the average orbit is. And so you can already see the family clusters show up a lot better. This is why we do our family analysis in proper orbital element space. Now, getting the proper orbital elements, however, is not simple. So there's two kinds of ways you can do anything. You can go for the analytic method or the numeric method. And the problem, numeric is great, except for you have to make approximations. You can't run an infinite numeric simulation. You can't have an infinite number of perturbing terms. And so you fundamentally are making assumptions that reduce the accuracy. The analytic, however, has its own set of problems. Right? It gives you an exact solution, but there are a few problems with it. And so it's pretty straightforward, though. You just take this Fourier expansion of the Hamiltonian, and it keeps going down here, what the terms mean, and then you can just solve for this, right? I mean, that's probably back of the envelope. But what you have to do is not just take the expansion of the Hamiltonian, but you have to do a multi-order expansion, both in inclination and eccentricity. And so typically what's done is a fourth order expansion in these two, which winds up being a to the power 2 of eccentricity and inclination, and it gives you this equation set. And so really straightforward, you just plug all the numbers in, right? And it looks simple. So this is why no one does analytical elements anymore, because it's really, really hard, and there's a lot of terms, and more to the point, you're only doing, this is a fourth order expansion, which is really second order in inclination and eccentricity, so it's only valid for orbits that have low eccentricities and low inclinations. It's not valid for objects that are in the near Earth population. And so you get great answers that are robust. The reason this is so complicated is that you have to remove, you can see this mu 5, 6 term here, and eta 6, and epsilon 6. These are the forcing functions from both Jupiter and Saturn. The 5 is for Jupiter, the 6 is for Saturn. So trying to basically remove the gravitational effect of Jupiter and Saturn from the gravitational orbit of this object in an analytical way. And it's really hard, as this shows. And we'll point out that a lot of the premier work on analytical proper orbital elements was done by Andrea Milani, who unexpectedly passed away last year. So he was really a leader in the field. And I think he was one of the only people who actually understood any of this stuff that he wrote down, because it's really hard. But it gives you this kind of answer. And so you can get these proper orbital elements for objects inside the inner main belt. But you can see, again, you have to do it in bins of eccentricity. You have to do it over only inclinations below 20 degrees. And the reason for that, again, is that the reason you have to limit your eccentricity window is a lot of these resonances. So the lines here represent resonances with Saturn and Jupiter. In this case, the G is the precession of the ascending node. So basically, if the orbit is tilted, how the tilt of the orbit oscillates around the sun. So the precession of the node compared with the precession of the node of Saturn. And so if your asteroid's node is precessing at a 2-to-1 or 3-to-1 rate with Saturn's precession, you'll get a gravitational bump to the orbit that will eventually clear it out. But that precession depends on the eccentricity of the asteroid. And so I forget which, I think this is, so this is like 0.05, 0.1, and 0.15. And so, this is just showing 3 steps in what is otherwise a smooth function. And so there's a lot of bookkeeping to be done to get these analytic proper orbital elements. So instead, now, a lot of this work you can see was done in the 90s when pencils and paper were cheap and computer time was expensive. Now it's the other way around, and CPUs are cheap, and people don't know how to write longhand anymore because we type everything. So we've all switched to numeric orbital elements now. And what you do for that is you just take the current positions of everything with the current oscillating elements and run it forward in time 2 million years in an n-body simulator. And you put in the masses of all the planets, and you put in, if you want to be really careful, the masses of Vesta and Ceres, and you do all of the gravitational perturbations, and you make your time step down to half a day or something, and you step all of these test particles through the solar system, and over about 2 million years, you can get rid of most of the short period oscillations. And so this is showing, again, from Knezovich and Milani's paper, this is how you filter those responses. And so what's going on here is, what it says is that for periods longer than a couple hundred years, take all of that Fourier transform. So this is basically applied to the Fourier transform. You do the integrations, you take the Fourier transform of your solutions, and then you filter it. So you take the long period stuff and you keep it. And the short period stuff here, some of it you keep at a low level, and some of it you drop. And so these drops here are resonance terms with Jupiter and Saturn. And so you can encode this in your filter, and you say, okay, I want to ignore these certain frequencies. So if my solution orbit has frequencies there, remove it. And then untransform, do the reverse Fourier transform back into orbital element space, and this gives you your numerical proper orbital elements. And so what's nice about that is you don't have to do a lot of math, or at least the computer does it for you. And what's also nice is you're not limited to low eccentricities, and you're not limited to low inclinations. And so here I'm showing the osculating orbital elements. And so if I now plug in the numerical proper elements, you can see that we get proper elements all the way up to basically where the main belt runs out. And we get them at high eccentricity as well. The downside is, and this was pointed out yesterday, these lines here of objects, and there's some buried in here too. You can see some vertical structure there as well. They are things that weren't properly filtered out by all my filtering codes, because the filtering assumes that nothing is directly in the 2-to-1 resonance or the 3-to-1 resonance with Jupiter. And so these things are artificially stable. And so numerical orbital elements need to be, you have to use caution when interpreting them. But they make life a lot easier. In particular, I like this family up here, And what was interesting about it is you can see it's above this 20-degree inclination cut. So it's one of the largest numerically. There's thousands of members of this asteroid family that no one had ever heard of simply because it was outside the plots. It was outside where we could do the analytical solutions. So again, there's good parts and bad parts to both of them. Nowadays, the Astis website, which Milani helped start, and now is being run out of Italy, continues to do regular numerical integrations. So I think it's every month or so, as a new catalog is published, they will do all the integrations and put out proper orbital elements based on that. So you can access all these proper elements from that catalog. So this gives us our plot of the main belt. So we're going back to this one now. And right, the primary structures are the gaps, the lack of objects, but our families show up as pretty nice clumps. But what do you notice about the clumps? What do we see about how the clumps are distributed? If you took a rock and you broke it up, you would expect velocities to be randomized in all directions, right, in x, y, and z, which would translate to a, e, and I. Do these look like spherical clumps? No, right? They look like they've been smeared in the a direction, right? They seem to be pretty tight. If you did a histogram in terms of inclination, they're really narrow. But some of these families seem to span the entire length of the belt, right? This one here, so there's a major resonance here and a major resonance here, and as I said, something hits a resonance gets ejected, but otherwise that spans, that runs from boundary to boundary. So what's going on here? Why are things being given a velocity preferentially to change their semi-major axis, but not change their inclination or their eccentricity? And the answer to that is what we call the Yarkovsky effect. And the basic summary of the Yarkovsky effect, and this is something that really has revolutionized the study of families since around the mid-90s. Basically, what you say for Yarkovsky is you have to remember that photons have momentum. And so, as your asteroid is sitting there baking in the sun, photons hit it and transfer momentum, and some of them are reflected off, and they transfer momentum the other way. So, as my solar photons hit me and are bounced off, I get a small momentum pushed backward. Because this is radial in terms of my orbit, the effect is that it makes the sun look like it weighs less. It makes the m of the sun slightly smaller. But in the Kepler's third law, p squared equals a cubed with the mass at the bottom, that won't change the Keplerian dynamics. The object will still follow a Keplerian orbit around the sun. It will just follow one of a sun that's a little bit less massive than the sun we actually have. Now for dust, that results in something called the Poynting-Robertson drag, right, where the velocity of a dust particle actually bends the light slightly, and so you get this relativistic shift. And so you can actually drag dust into the sun. Asteroids are too big for any of that to matter. But if the object is rotating, things change a little bit. As the sunlight hits me, I warm up. If I rotate a little bit, then, much like on the Earth, my afternoon side is going to be warmer than my morning side, right? Because my back is coming from cold, this is coming from warm, and so the peak of the thermal heat gets dragged a little bit this way. When I emit thermal radiation photons into the void, they're going to come on this vector. Now, you do your vector component, most of that is pointed back at the sun, same effect, makes the sun lighter. But a very small amount is pointed along my orbit. And so what this acts like is a very gentle photon thruster that either speeds up my orbit, or, if I'm rotating retrograde, slows down my orbit. And so objects will very slowly spiral out or spiral in based on what direction they're rotating with respect to their orbit. Prograde rotation results in outward mobility. Retrograde rotation results in inward mobility. Now, the emission, my thermal emission goes as d squared, right, because pi r squared facing the void, and my mass is d to the negative 3. So the Yarkovsky effect goes as 1 over diameter for a given distance from the sun. So that means that smaller objects get a faster kick than bigger objects. And so that spread we saw in the families, where the small things were farther than the big things, is exactly what you would expect from this Yarkovsky photon drift. Now it also goes as, it effectively goes as flux, because you have solar flux instant on you, which causes a thermal emission, and then you have the luminosity is T to the fourth, and then T causes your own temperature, and then you have a subsolar temperature. So it's roughly goes as 1 over r squared in terms of distance to the sun. So what that says is that the Yarkovsky effect is significantly more powerful for something in the near-Earth population than it is for something in the Jupiter-Trojan population. The farther you get from the sun, the weaker this effect is, but it's kind of in a sweet spot for the main belt. Now, I just want to cover a little bit of background on who Yarkovsky was, because this is a really fascinating story. So this is they actually found a portrait of Ivan Yarkovsky, and it turns out he was a Polish-Russian railroad engineer who dabbled in science and put together a pamphlet around 1900, written in Russian and published there, and would have otherwise been lost if not for Opik, who in 1951 says, "Oh yes, I remember, I read a pamphlet in Russian about this 40 years ago," and brought it back up together. And so he was able, and much to his credit, credited Yarkovsky with coming up with this idea first, which is one of the most impressive parts of this. And then it turns out that other people had been thinking along these lines. Ryzhevsky had been as well. Paddock in the United States had been working on this. But it was Yarkovsky who first thought of this idea that the thermal radiation might affect the orbit of a body. Now, if you actually read this Beekman paper, it was in the British Astronomical Journal. And so he actually found a biography of Yarkovsky that had been written but never published in Russian with the widow of the person who'd written it, and so was able to actually get a lot of the data. Yarkovsky, and he actually found the pamphlet that was in 2002. They said, "Oh yes, this pamphlet has recently been lost." Consigned to oblivion. Pamphlet. He read the pamphlet, and the pamphlet is lost. It turns out he found the pamphlet in Moscow somewhere, and so that's a photo of the page of the pamphlet that was published in 1901, talking about this effect. Now, Yarkovsky, this was written in the early 1900s, so Yarkovsky did this as a way of trying to explain why asteroids and comets weren't being slowed down by the ether they were moving through as they orbited the sun. Right? Because in 1900s, the solar system was full of ether. That's what carried light around. And so clearly, if light can move through ether, it must have an effect on the orbits of bodies, and so he was trying to come up with forces that could motivate something to push against the ether so they didn't spiral into the sun. But it turned out to be prescient for reasons he never could have expected. Looking into this, though, I think this is the funniest thing I ran into, and this is why you don't send preliminary things in, is I was looking for other mentions of Yarkovsky, and Dale Cruikshank in 1977 put this into a proceedings for a journal, which was, "I'm not going to have time to draft an abstract, so go to press without me, sorry." And so instead of going to press without him, they put his little one-sentence thing in there and published that in the proceedings. So always be careful what you send in for your proceedings and your abstracts, because someone's going to find it, 50 years later and make fun of you. Dale's a good guy. So what does this look like then? So this is Yarkovsky effect in illustrations. You have the sun, you have the object rotating, the thermal vector goes this way, so you get a recoil motion that way. And this occurs over long periods of time around the sun. And so you effectively have this spiraling. Now, if you look in Bache's 2000 paper, there are two effects. One is this, the diurnal Yarkovsky. That's a result of the day-night dichotomy and the thermal wave being pulled over. There's another one which is a seasonal Yarkovsky. And you can imagine that if I have a pole, if my rotational pole is tilted with respect to my orbit, then in the summer on this side, I have excess heat and I get pushed this way. And then when I come around to the far side, to my other pole gets heated, and you can imagine you get an up and a down motion, and that should change the inclination of the orbit. But it turns out that, for reasons I'll get to in a little bit, the seasonal Yarkovsky happens very rarely, if ever. And the diurnal one dominates. And what was most interesting is, you saw like the OPIC paper was written in the 50s, a lot of the work was done in the 70s, but it wasn't applied to asteroids until the 90s. And the reason for this is all of the early work was looking at its effect on meteors, meteor streams, and in the 70s on spacecraft. And so small bodies, no one thought they could affect anything this big because there are collisions within the main belt, as we've shown, and stuff gets reoriented. And there shouldn't be this much of an effect. No one really thought about, okay, how long, Yarkovsky should work on day or year timescales for, pebbles, but 100 million year timescales were just considered to be too long to be feasible. It wasn't until the 90s when we started to realize exactly what they could do in terms of our study of families. So here's some of the equations that you need to use to calculate the Yarkovsky effect. And so it depends on the angle of rotation, where the seasonal force is, the direction of the sun, all of this. You can skip this for now. I just included it to show that there's a reason that you write this once into your computer code and then forget about it. And it's because you don't want to do this by hand. So very good software will do all of this work for you, but you have to learn it once. So learn it once and then don't worry about it after that. Just make sure your code is right. But there's a secondary effect here. And it kind of comes out of this right here. You can see how Yarkovsky is calculated. Everything assumes a sphere, right? Spherical chickens in space, the great physics problem. Everything's a sphere, so everything is incident directly through my center of mass. But what happens if it's not? What happens if you're not a sphere? What happens if you have these two little wings here? In this case, Rubin Cam just put prisms on the side of a sphere, and then you redo those equations. And you say, what is my effect on my body now? Now that I'm not having everything being radial from my center of mass. So what do you get? So let's say you have the photon sitting here and bouncing off, and you have photons sitting here and bouncing off, and then you have thermal emission in these directions. If you have a vector coming out of this thing, out of this prism, off axis, what does this do to your body? What do you get when you have a vector that's not emanating from your center of mass, that's emanating off in a different direction? Tumbling. You get a torque, right? You have a vector, you have an R and a V, and you get a torque. And so if you have a sphere, the Yarkovsky effect works. If you have anything non-spherical, in addition to the Yarkovsky effect, you can have torques being instilled. And so this can cause objects to spin faster. It can cause them to spin slower. It can set them tumbling. And it can change the sense of rotation. And so if you go through the equations, what you would expect to see is objects. So you can imagine that if you just have a random set of asteroids and they're spinning randomly with respect to their orbit, some of them will have their poles changed into the plane of their orbit, and some will have their poles changed up. As things get their poles changed up, they stick there. Things that go here will go across the zero and then get stuck at the bottom. And so what you would expect to see then is asteroids having their poles aligned with their orbital plane. And it turns out that we see that. We see objects with poles that are aligned. So this is all, so Slive did this for his thesis, and this is a set of objects in the Coronis family, and did 3D shape models of a bunch of these asteroids. And when you take those light curves and you do those 3D shape models, in addition to a 3D shape model, you also get a pole direction. From those pole directions, if you look at this family, he saw that, well, that's weird. All the things orbiting that were rotating retrograde had their poles pointed at one direction, and all the things rotating prograde had their poles pointed in a different direction. And in fact, the majority of these had their poles pointed right at Cassiopeia, which he said is either a random or a sign that the answer to the great question of life starts with a W. But we see alignment. We see the Yorp aligning things. And what that does now, if your poles get aligned, Yarkovsky speeds up, right? Because now, instead of having, if I'm rotating perpendicular to my plane of orbit, then I have the maximum force from the Yarkovsky effect. If I'm rotating a kilter, then the force will be lesser. And so Yorp also is stronger the smaller your body is. And so what you get is effectively an acceleration of this effect, where the big objects don't have their orbits realigned by Yorp and don't move much in their orbits, and the small stuff gets their orbits aligned and gets accelerated, spread out in some major axis space. Now, Yorp effect is a awkward acronym for 4 of the people who worked on it. That is Yarkovsky, that's O'Keefe, that's Radzievsky, and that's Paddock. You don't need to remember that. That's just the 4 people. And what's really nice is it makes an acronym that's pronounceable and yet sounds somewhat funny. So it's just overall entertaining and pleasant. So what this tells us now with Yarkovsky and Yorp is that when we have families, they will evolve over time. And so let's start out with a generic asteroid here. And the asteroid breaks up, right? So it shatters and pieces of it fall apart. And it could have been hit by an asteroid, it could have been hit by another smaller object, it could break up for other reasons, but for some reason the asteroid breaks up. Does anyone know what this is? No one? Do you know what this is? Anyone? You have to play old video games. Go play Asteroids. It's a good video game. This little spaceship that you blow up the asteroids with. Go play video games. So the asteroid breaks up and starts with a dense cloud of objects. Now, obviously, this is happening in 3 dimensions, and I have this on a 2-dimensional plane. But over time, as Yarkovsky kicks in, the objects will spread apart, with the smaller objects spreading faster than the bigger objects. And so they keep spreading, and they keep spreading, and then eventually, the small ones hit one of the resonances with Jupiter, one of these mean motion resonances. And then they get ejected. Very quickly, a resonance with Jupiter is a lot like a kid on a swing. If you push every time, and you're not gentle about it, the swing goes higher and higher and higher, and then your kid goes flying off, and you get yelled at by your spouse. It's all terrible. But the same thing happens. Jupiter pushes, 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 and eventually the object, the eccentricity grows and grows and grows, and the object hits Jupiter or hits the sun or is ejected from the solar system. And so these things get flung out. And so what this lets us do is figure out how long these things have been drifting. Because if you know how big that object is, and you know how big that one is, and you're pretty certain that these two were from the same family, then if you just measure that distance and that distance, you should be able to back the movie up and figure out when were they all at the same point. Now, for very young families, objects a million years, a couple million years old, you can do this numerically and precisely. And so this is a really interesting piece of work that David Nizvorny led on the Cairn family, which is actually, Coronis is one of those giant families, one of the first ones that Hirayama found. Within Coronis is an asteroid called Cairn that has a smaller family associated with it. So a member of a family got hit more recently and caused its own little mini family. And so if you take the orbits of these objects, and so in this case, you take the perihelion of the longitude and the nodal longitude, and you integrate backwards. Now again, this is not in proper elements, this is in osculating elements. You actually do the backwards integration of the osculating elements from today, and you make some assumptions about what the rotation state is for the ones you don't know, and you do the Yarkovsky calculations backwards, you wind up getting all of these orbits converging at a single point of time, about 5.8 million years ago. And what that says is that all of these asteroids lined up in space and time at one point. This is exactly what you expect from a massive breakup. So for young families, you can do the direct backward integration using your n-body code and get an answer. For older families, we can't do that. Because as you go back in time, first off, you have to make these assumptions. Which way is the Yarkovsky effect going? If you have more than 30 objects, it's harder to make those guesses right. And you start getting chaotic effects in the solar system. If you have objects in your family that hit one of those resonances and get ejected, now you're losing information about your family. You're losing some of your determination. But what you can do instead is go forward. So you say, I think the parent was around here. I will simulate a breakup. I'll make 1,000 test particles here. I'll give them very slightly different initial conditions. And let's see where they go. Let's blow up an asteroid. And so this is what you get for the Yarkovsky family. Or for the Euphrosyne family. And so this is showing proper semi-major axis and eccentricity done over around 800 million years. And what happens is, the first thing you notice, and this will repeat, is that the family was pretty big to start with, and drains. Over 1 billion years, you lose a large fraction of the original family members. And many of these go into become near-Earth objects, into near-Earth object space. So the families are one of the key sources of the objects that come close to the Earth. Because small objects get cleared out of near-Earth space. And primordial small objects get cleared out of the main belt on gigayear timescales by the Yarkovsky effect. So anything that's small today had to have been born relatively recently. And the place you give birth to young asteroids is within families. And so you can see in the simulation, if you watch closely, you can see some of the small objects. The small objects are drifting faster here. These big guys don't move very much. But you can see long-term variations, right? As things cross over these very weak high-order resonances, some of them get shifted around. Follow this one, you can see it's crawling up, and it'll probably got ejected right there. So there's a lot of stuff going on in the belt. And this is why you can't backwards integrate everything. After a million years, it gets very confused, and chaos takes over. There's a lot of chaos in our solar system because there's a lot of stuff going on, and a lot of uncertainty. Even if we know where the planets are to within a few meters, those few meters propagated over hundreds of millions of years can cause large uncertainties in what the perturbations will be on long timescales. So instead what you do, and I'm sorry this movie doesn't work, I think I didn't copy it right, is you take your known asteroid family, which is the black dots, you simulate your asteroid breakup, and then you let it evolve forward, and at certain time steps, you basically write out the position of all your simulated particles at time steps, and then just watch as these objects drift, and you compare the distribution of known objects to your distribution of simulated objects. And by doing this, it'll start out that you can see at time equals 0 here, these red points are over-concentrated. Right? They look to be kind of on this kind of path here. The black points are more spread out, so we would have to evolve longer to get the points to match. If you go too far, then the red points are filling up this space where we don't see any family members. And so, now one of the assumptions you have to make is, when I say simulate a breakup, that's pretty hand-wavy. What that really involves is, what ejection velocity do the particles leave with? And you can assume it's leaving in a sphere because it winds up, if you do some test, it doesn't really matter what direction they leave in, but what the distribution of velocities they leave with, right, if you have if you're fired out from the family very quickly, it will start with a much bigger initial spread than an object that's very gently broken up. And so by testing a range of breakup velocities over hundreds of millions of years, and comparing it, and so this is basically a chi-squared comparison, comparing it with the known family, you get a region here that says, okay, this family most likely is around 100 to 150 million years old, and most likely was ejected with pretty low rate. Right? It wasn't fired out up here. It was probably coming in down there. And so this is where that peak here, in terms of quality of fit, right around 1.2, 1.1 billion years, and then with a ejection velocity of around 50 meters per second, and a York strength of close to 1. This was trying to, early on, it was trying to guess how efficient was York. How quickly did York realign the rotation states of these objects. We now have measurements that show how efficient this is, and it does tend to be right around this one parameter here. So, but something else to note here is that as we get out older and older timescales, so we're getting up to 1 billion years, you can still get a somewhat good fit, but it's starting to spread out. You're starting to lose definition. And so this method of age dating only works for about 1 to 2 billion years. Older than that, and you just start running out of space. The objects have already expanded so far, they've hit the resonances, and so you start to lose resolution in your family age data. But this is how you can use these simulations and the Yarkovsky effect all to work together to give you about how old a family is. One other interesting thing you can look at is, based on the size distribution of a family, how many little pieces there are versus how many big pieces there are, what kind of breakup happened? How did the asteroid actually shatter? Because there's going to be a very you expect to see something very different if you took a big asteroid, hit it with something small, and just knocked off a few pieces from a big crater, versus if you had an asteroid that was hit by something almost the same size of it and broke it up utterly, where there is no big parent left. And so you can see kind of a simulation of a cratering event where you have one big 100-kilometer asteroid remaining, and then a bunch of shrapnel that follows this kind of concave shape, versus this super catastrophic event where you basically take two things about the same size, ram them into each other, and they're both totally gone. Right? There's no like 50-kilometer parent left over. The biggest thing remaining is around 9 kilometers, even though you started with a 46-kilometer impactor. And so by looking at the size distribution of the families, you start to be able to see what kind of impact was it. And this can help also inform the age dating. So you can look at what kind of impact, how old is the impact, what sort of, what's this history that we're looking at. And so we did this with WISE. This is an eye chart, so you don't really have to pay too much. You don't have to find anything specific, but I just want to point out that some families you see here have this long tail where there is one big parent and you start to get this size distribution. Other ones don't have a single big parent, instead are just a bunch of shrapnel. And so one of the EOS is a great example of that. So this is number of objects up here and size down there. It's a cumulative histogram. And so the height of this is just the number of objects. So you can see the EOS family here has 5,000 members in it, and the biggest thing that's remaining is around 30 kilometers. So most of the mass is in small dust. We can also look at, take it for the same objects, what's the distribution of albedos within the family, and what we see is that they're all, so this is again number of objects and log of the albedo. And unlike what we saw with the main belt in general, where we had two humps, a low albedo and a high albedo hump, the families are uniform. And this is exactly what you expect from a single object breaking up into chapters.
What's the red line?
The red line is just Vesta plotted against all the other ones, so you have something to guide your eye with. And so someone asked me about this yesterday or 2 days ago, but the 3.4 micron albedo here, if we plot that up for the families, because of selection effects, we don't have as many low albedo families in this plot. We only have Themis, and then we have this very unique peak here, and all the objects we see with this albedo are associated with the EOS family. And then you have a bunch of families in here, and those are all your S-type families. And so what this plot is telling us is that that family, this 221 EOS, is somehow compositionally unique from everything else we see in the main belt. There's something really strange about it. And so here I'm showing visible albedo log against, so this is the slope of that size frequency distribution. One of the questions we asked is, how does the change in number of objects as a function of size, when that grows, is that different for bright objects and dark objects? You might imagine if your low albedo objects were very loosely held together, they might shatter more easily than a high albedo silicate that you think is kind of a rock. So you might expect to see a difference in slope, and we don't see one. So what that tells us is that it's not necessarily the composition of the asteroid that determines how it breaks up. Or rather, it's that the internal structure of all these bodies are comparable. That whatever they're made of bonds together in similar ways. You don't necessarily expect carbon-rich asteroids to behave, to be bonded or break up differently than silicon-rich asteroids. And it could be that it's because compositionally they're indistinguishable, or it could be that they've been processed heavily. Over 4 billion years, enough stuff's run into them that they're all shattered entirely inside. One of my favorite things we found from asteroid families is this. So when you do your hierarchical clustering method, it works great in a vacuum. But you can have cases where you have 2 or 3 or overlapping things brought together. And so for a long time, this was called the Nissa-Polana asteroid family because there are 2 big objects in it, Nissa and Polana. And now that I've shown you before, you can see kind of there's one wing here, there's another wing here, and you can see almost this bifurcation in the asteroid family here. And so for a while, people assumed it might be 2 different compositions, or something broke up, or maybe you had the mantle and something happened, or it was one object that was broken up twice and so evolved differently. But when we use our albedo information, we see this. And so what we actually got here is one family that's low albedo, an entirely unrelated family that's high albedo, and they just happen to overlap in 3D space. They're just touching each other. And so when you do your hierarchical clustering method, they wind up connecting. These vectors pull them in together. Here you can see that the bright stuff makes kind of its own little V shape here, and then you have a low albedo V shape here and a low albedo V shape there. And so this is just to point out that the physical properties offer us a new dimension to study the families, and also shows why we need to start to move beyond hierarchical clustering method into some new method of linking these things together that can take into account all this new information we're getting. And just to make a point of it, right, asteroid family collisions have been happening over the last 4.5 billion years, but that doesn't mean they're not happening today. So we still see collisions happening in the main belt every day. Well, not every day, maybe once a year or so. But as we look more with bigger telescopes, we will see them more often. So this is a comet-like asteroid 2010 A2. And so it was this object that had an asteroid-like orbit, looked like it was a normal main belt member, except had this long dust tail. And so when Dave Jewett and his collaborators turned Hubble Space Telescope at it, you get this shape here. That does not look like any comet. But what it really looks like is something ran through the other one, and it made this big X in the sky as material was ejected in a cone in both directions. And so what we're seeing is a catastrophic breakup, just like we have for these giant families, like the EOS family. Absolutely catastrophic breakup, just on a very small scale. So this is, a couple 100-meter object that was hit by something that was a couple meters and utterly shattered. And what I'm really excited for is that as we start to learn more about the contents of the main belt, hopefully someday soon, maybe in the next 30 years, maybe in the next 50 years, we'll start to be able to predict impacts. We'll know both objects as they exist and be able to say, these are going to hit each other in 5 or 10 or 20 years. We'll be able to study them before and after, and possibly, funding willing, send a spacecraft to watch the impact, to see what happens on these catastrophic scales. This is asteroid Sheila. So this was just a year later. A small object hit one of the biggest asteroids in the solar system. So this is 596 Sheila. It's one of the early ones that was discovered and was included in Hirayama's analysis. But you can see this little mohawk of dust shot off of it. It was just an instantaneous event where something small ran into Sheila, leaving a big crater on it. Right? This is a catastrophic impact and a cratering impact. They're still happening today. And so what we see in the near future is going to help us learn more about families and study them even better. So that's the end of my lecture for today. Tomorrow I'm going to be giving an overview of the planetary science results from the NEOWISE infrared space survey. So this is the mission that I've been working on for the last 10 years. And so, I'm looking forward to sharing that with you, as well as what we're going to be doing with the next generation telescope NeoCam. So thank you.
When you analyze the size frequency distribution with the NEOWISE data, how do you treat the incompleteness of the sample?
We haven't yet, because this is really hard. So tomorrow I'll talk about, so when you take a size distribution, what you need to know is not only the objects that you know about, but what are you missing? Because you're preferentially going to miss small objects. So for an object population like the near-Earth objects, you take the whole population at one go, and you can debias it. You can say, here's what my survey saw, here's what my survey should have seen, so I know what the real population looks like. We've done that with the Trojans as well. With the main belt, we haven't gotten to that yet because you need to debias every family independently, and then you need to debias the background. And you also need to account for the fact that your associations between family and background are incomplete and possibly in error. And so it winds up being a difficult mixing problem that you have to unmix and debias and put back together. So we haven't fully done the debiasing yet. What we can say is that based on the objects that we discover, we can set limits to, all right, with the smallest object that was discovered by NEOWISE, the largest object discovered by NEOWISE was 10 kilometers. There was just one of them in the outer edge of the main belt. So that means effectively we're complete in 10 kilometers throughout the belt. For different populations, you can look at where your size frequency distribution turns over. And if you just say, okay, I'm going to cut at 50% and only look at the stuff bigger than that, you can make a rough debiasing of it. But a more complete debiasing is needed, absolutely.
Thank you for that.
Yeah.
So that plot that you showed with the size distribution of the families, I think it was this one.
The eye chart, yeah. Sorry about that.
So, for example, I don't know if you expect some of them to be a mixture of collision and cratering events.
Yeah.
Because, for example, you see some of those, for example, Battistino.
Yeah,
The blue ones, actually,
Yeah.
that have these cuts.
Yeah.
They have no big objects.
Yeah, there's no big objects, yeah.
And then you have other ones that have big objects and
Yep.
a mixture of them.
Yeah.
I don't know if you expect some of them to be mixture of cratering and collision.
Statistically, you would expect, looking at the way how often things get impacted, you don't expect a single big object to be hit more than once or twice in the age of the solar system. We know Vesta was hit twice because we flew by it with dawn and we see a giant crater in the bottom, which caused this family that's 1 billion years old, and we see another giant crater underneath that's 2 billion years old. And you can start to see, not in this plot, but in like the semi-major axis versus size plot, you can start to see echoes of maybe there's a second older family in there. But nominally, you would expect each object to only be hit once, really, in a family-forming impact.
You mentioned the determination of families from orbital elements.
Yeah.
It would be useful to also include colors to this and make some use some kind of clustering algorithm.
Yep.
Improve perhaps.
Yeah, so when we first published the WISE albedos, the first thing I did was include albedo and just do a family analysis based on albedo, and we're able to get more family, maybe a dozen families that were missed in other surveys. And subsequently, the ASTIS folks have started incorporating colors. The problem is that we have 700,000 main belt asteroids in our catalog, albedos for 150,000 of those, colors for around 100,000, and that set doesn't overlap. And so it becomes a problem of how do you deal with the objects that you know about but have incomplete information on. And so there's one researcher who just gave a talk at DPS about using cladistics, which is a technique used in anthropology and in zoology, basically, of gathering creatures together based on their DNA and their and physical characteristics. And so this has been used for 50 years in biology. But he's trying to apply this to families where it can account for, all right, we have some knowledge, but not all knowledge, and some things don't have other things, as a way of doing a probabilistic thing. The problem is that you immediately get into, all right, I now have to do a probabilistic association, and when I do that, how do you then parse it into something like this, where I can say, all right, I want to study how this family compares to that family, but how do I deal with things that might be a member and might not be a member? So, yeah.
Artificial intelligence, if you are using some kind of machine learning as well to study the kind of doing this clustering or searching families.
Yeah, not yet. We've looked into it, and there is a lot of potential avenue there for especially image recognition. I showed, here, right? by eye, you can already see that, okay, that's a cluster, there's something here, right? There is a lot of potential for using image recognition, but it's not super fully developed. Most of the image recognition software right now is about like, find the person's face in a picture, find, is that a car or not a car? There's not a lot of really good, like Silicon Valley isn't looking for how do you define the edges of a fuzzy boundary so well, but there is some work being done on that. So I don't think it's there yet, but I think it's in the near future. Absolutely a good possibility.
I think that somebody that is trying to work with the identification of asteroid families from using machine learning is Valerio Carruba.
Yes.
At Carruba. Just one comment. One of the problems that you have when you combine orbital elements with physical properties is that you, unavoidable, you will detect only homogeneous families.
Yep.
You will not be able to detect an inhomogeneous family if any exists.
If any exists, yeah.
So that is actually a problem.
It is.
When you start to combine different things, you may reveal some interesting things, but you may hide other things.
Yeah, a lot, and that's true with any kind of survey, right? If you only look for what you're expecting to find, you won't find the stuff you didn't expect. So, yeah, absolutely. Like, one of the things that comes to my mind immediately is, you know, if we can fold diameter in, right? Because if we say, all right, this is the parent body, and we do a clustering model that goes out from here, I can say that, all right, if this is my parent, there's no way that this could have moved over there from Yarkovsky in the age of the universe, or in the age of the solar system, or in the age of anything useful. So I can, even if this would have linked up via that chain, I can reject that link based on size and, you know, a priori knowledge of how Yarkovsky works. So I think there's an avenue forward for there in that respect as well. So, but you're right, you have to make sure you include the right sorts of data and don't bias yourself